In this part of the chapter, you will be learning a great deal of information about reaction kinetics. We are going to start with the time-dependent form of the rate law and its subtopic, the half-life concept. Then we are going to explore the effect of temperature on rate constant using the Arrhenius equation. Afterwards, we are going to investigate the molecular events taking place during a reaction through the study of reaction mechanisms. And finally, building on our understanding of mechanisms, we are going to discover how catalysts work. Rate law is an equation that relates the rate of a reaction to the factors that affect it. It calculates the rate of a reaction, all right, but it is limited in its scope. It does not contain a time-concentration relationship. Such a relationship is essential for industrial applications of chemical reactions because we want to know for how long a reaction needs to run for a certain amount of reactant to be converted to products, or we want to know how much of a reactant remains at any time during the reaction. The relationship between concentration and time is known as the integrated rate law, and now we are going to see how we can obtain it. Zero order, first order, and second order reactions have different integrated rate laws. Each equation is derived from their respective rate law using calculus. You are not responsible to know these derivations, but you are required to know the meaning and the use of the integrated rate laws. There will be certain terminology that needs to be well understood before we go further. In square brackets, A means the concentration of the reactant A. T is short for time, and concentration of A sub 0 is the initial concentration of A at time equals 0 in the beginning of the reaction. Concentration sub T is the concentration of the reactant A at time equals T. T is a variable, and K is the rate constant. Let's start with a zero order reaction. A zero order reaction has its rate law equal to the rate constant. Also, rate is equal to the negative of the change in concentration of the reactant per change in time. Equating the two rate descriptions, we get rate constant is equal to negative of the change in concentration per change in time. Let's rearrange this equation to this format and then integrate from time equals 0 to time equals t. We get an equation that is linear, and then rearranging that equation for concentration at time equals t gives us the integrated rate law. This equation calculates the concentration of the reactant A along this line with changing time. The starting point is the initial concentration of the reactant. At any given time t, the concentration of the reactant is equal to initial concentration minus the product of the rate constant and the time elapsed. For a first order reaction, we start with its rate law. We're going to equate the rate law to the definition of the rate. We are going to rearrange and again integrate from time equals 0 to time equals t. The solution of this equation gives us the integrated rate law, such that the natural logarithm of the concentration at time equals t divided by initial concentration is equal to the product of negative kt. This equation calculates the concentration of the reactant A along this line with changing time. The first order integrated rate law relates concentration and time. You can use it to calculate time if you know the concentrations. But due to its logarithmic nature, it is convenient to rearrange it to solve for the terms inside the logarithm. This is the same equation, but solved for concentration. Use this form of the equation if you are calculating concentration. The derivation of the second order reaction integrated rate law starts with its respective rate law also. equating the rate law to the definition of rate, and then rearranging and integrating, we obtained its own integrated rate law. It gives us that 1 over the concentration of the reactant at time t is equal to the product of rate constant and time plus 1 over the initial concentration of the reactant. Here is the summary table for integrated rate laws based on the order of the reaction. They allow us to calculate time and concentration during the course of a reaction. It is very important to note that the correct equation must be used for a given reaction. For example, if the reaction is first order, then the first order integrated rate law must be used to get the correct answer.